All right, at length throughout calculus, you've dealt with the integral as being something that measures area, and now we have ways to use the integral to measure volume. And now we're going to show you that you can use integrals to measure length. So we'll have all three dimensions, if you will. We'll have length, area, and volume covered by what calculus is able to compute. All right, so anyways, let's start with an example to motivate what I'm going to do. I want you to consider a circle. Of radius 6. I'm not going to go through the effort of pulling in a circle from somewhere else. I'll just try to draw a rough sketch of a circle. The radius is 6. The circumference is C equals 2 pi r. So this is 2 pi times 6, which equals 12 pi. What is the circumference? The circumference is the length around the circle. In other words, if I were to take and just cut the circle in the spot, suppose so if I cut the circle in one place, let's say one point, and then roll it out, the resulting line would be 12 pi in length. So basically the idea is this: got my circle, radius of 6, I make a little snip here, and then roll it out until I get to that snipped point again, and that would be 12 pi, would be how long it is. The circumference of a circle was the very first time you were probably introduced to something called arc length. The circumference is nothing more than a term, a specialized term for a circle, or any figure that's closed like this. But the arc length will deal with the length of the curve under discussion. So in this case, the curve would have been a circle. Now, I would like to use calculus to show you how to derive this particular answer. And I'll first start with a circle. So, if you look at, consider, let's see, x squared plus y squared equals 6 squared. That's a circle of radius 6. So we'll call it the circle of radius 6. Centered at the origin. Okay, I put the numbers there because my circle doesn't look so great. What I'm going to do is actually not work with the circle itself. I can't use calculus to work with the circle because the first thing calculus wants to do is deal with functions in one way or another. This is not a function, of course. It fails the vertical line test. However, I could work with just like the top half and then simply multiply my answer by 2. So we will deal with just the top half. So if I can figure out the length of this, then I simply multiply by 2. Now the equation, I'll deal with the equation a little bit later. Do I want it? Do I want the equation? I will. I'll tell you what. The top half, the formula is y equals the square root of 36 minus x squared. Now, as we usually do, I'll try to do these rectangles, they call the right rectangles, and try to use these in a way to measure what I'm trying to do. Well, you get the idea. This will go on and on and on throughout the length of the problem until you get to the very end. Boom. All right, so what we typically do then is perhaps we would rotate this around. Sorry, didn't mean that. Actually, try to use these lengths, the lengths or the widths of each of these rectangles, add them up, and then as we allow the rectangles to get smaller and smaller, it's going to conform more perfectly to this curve. Well, if each of the rectangles is of width delta x, then the sum of all the widths is, so delta x, all these are delta x. That was for convenience. We would do summation delta x, k equals 1 through n. So this would be, remember, this is, the beginning is x sub 0, the end is x sub n, you get x sub 1, x sub 2, x sub k, etc., etc. Well, they all had, I was only concerned really with using these horizontal lengths because as the rectangles get smaller, the lengths would get shorter and they would become closer and closer to the shape of this curve. Unfortunately, when I add up all the delta x's, that means this length plus this length plus this length plus this length, plus this length plus this length. Well, it adds up to 12. And in fact, it doesn't matter how I do that. If I do them all in the same, it does actually. If all of them have the same width, then I have something like this. Now then, if you do the limit as n goes to infinity, it's still going to equal 12 because the limit of a constant is a constant. Well, unfortunately, even if I multiply that by 2 times 12, that's 24. What is the circle's circumference is 12 pi, which is more than 36 even. So what we have here is 24 does not equal 12 pi. So what we're doing for the other stuff is not going to work here. So we need to adopt a new method. So a new method is in order. this time we're gonna, let me redraw this circle, or the top half of it at least. And let's make our points. This is always what you do. You do x, you actually partition the interval first thing. And you know how this goes. You know, at some point I'm going to get to say x sub k dot 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 dot, and then the very last one is x sub n. So x sub 0 in this particular case is -6. X sub n equals 6. Looks like the following. Let me give myself lots of space. The new way is to do it like this. You lay down your points, or your numbers. x1, x2, x3, xk, xk plus 1. That'll be the one that I really want to deal with. xn. What we do now is we're going to go and put points on the curve like we did before. So these points here, this would be like x1 comma f of x1, and this next one would be x2 comma f of x2, and then the next one would be x3 comma f of x3. You get the idea. So when I get to xk, and then xk plus 1, I'm going to have xk comma f of x sub k, and the next point will be x sub k plus 1 comma f of x sub k plus 1. Now what we're going to do is, instead of doing horizontal anything, I'm going to connect each subsequent point with a straight line. I'm not sure if I can make it visual here, but I'll try. I want to try to connect each of these with a straight line. So maybe a little bit more detail is in order. Let's take this and blow it up. Better. So what I want really is the length of that. Now the curve comes in, the circle comes in something like this maybe. But anyways, what's the length of that thing? What is the length of that hypotenuse? Let's call that L. Well, let's see what we have here. We have from one succession to the next, what you're obviously going to do. There's L. This piece here is x sub k plus 1 minus x sub k. And then what would the height difference be here? Well, we would have the higher one here in this case is f of xk minus f of xk plus 1. So I'll draw that again, but much bigger. Calculus is the art of zooming in and zooming in and zooming in and zooming in. So this up here was f of x sub k minus f of x sub k plus 1. Down here was x. How'd this one go? This distance, if you're going to keep it a positive distance, would be xk plus 1 minus xk, so it's switched there. And there's L. What I'm going to do, well, let's leave it like that. let's go ahead and use the Pythagorean theorem to get a handle on L. So we know that L equals the square root of this squared plus this squared. I'll put the x's first. Now, what I want to do is factor this out. So here's what I did. I factored out x sub k plus 1 minus x sub k squared. When I do that, it leaves a 1. But you have to consider that you took it also from this piece, so that will leave this quantity divided by this quantity. That's why I have this here. It's squared to make things simple. Then when you factor it out, whenever you take the square root of something squared, it's not just the number itself, it's the absolute value of that number, just in case that number is negative. Now I can fix a few things here. Because x sub k plus 1 is bigger than x sub k, I can drop the absolute value. Not only that, inside of these parentheses, I can rearrange the order of the numerator so that it matches the order of the denominator. Okay. Now that was the length of a small little piece of it. To estimate the length of the curve, add up all those line segments. Or at least their lengths. So you're going to do something like this. Summation k equals 1 to n, sum 1 plus f of x sub k plus 1 minus f of x sub k all over x sub k plus 1 minus x sub k, that quantity squared, times x sub k plus 1 minus x sub k. I think it might not be a bad idea at this point to remind you that x sub k plus 1 minus x sub k is delta x. Now let n go to infinity. What that means then, x sub k plus 1 minus x sub k is going to 0. So what does that tell you about this quantity in here? If you look, if this is going to 0, and this is going to 0. We're talking about differentiable functions here. I don't know if I've ever mentioned it in the whole semester yet, but we're assuming whatever we need to get the job done. In this case, f will be differentiable. So this here, if you can remember, this is the derivative at x sub k. So we're going to get this. Summation k equals 1 to n. We get the limit. and we know what this is. This will be the integral from a to b, which in this problem, where did this thing start? This thing started at -6, and it ended at 6. So we have -6 to 6, and this is the part I was telling you about. This stuff here, since x sub k plus 1 is going to x sub k, that quantity is going to 0. This quantity is approaching the derivative at x sub k. But then, when you switch to the integral, you drop the x sub k part of it. That quantity is actually squared. Let me increase the vinculum. And delta x becomes dx. Well, what was f of x equal to? F of x was equal to the square root of 36 minus x squared. So its derivative, remember to use your chain rule. This is like 36 minus x squared to the 1/2 power. So you can get 1 over 2 radical 36 minus x squared. Then take the derivative of what's inside. So the derivative of 36 minus 2x squared is -2x. So that's just an aside. Let me come back to my integral here. Notice that the 2's cancel, and you'll have -x over 36 minus x squared. That quantity is squared, dx. Now when you square this, of course, the negative goes away and you end up with a common effort to simplify things is to get a common denominator. So I'm going to write this 1 as being 36 minus x squared over 36 minus x squared. Okay, and then this equals and then of course the square root of 36 is 6. I'll pull that out front. Alright, when you're doing a problem like this, there are a variety of ways you should probably recognize what you're dealing with in this situation here. And what we have is 36 minus x squared. You may, if you look in the back of your calculus book, they probably have a table of integrals. Or maybe you were supposed to memorize how this worked out or something along those lines. But you should have remembered, there's a 6 out front, that this guy right here was 1/6 arcsine of x over 6. And that extends from -6 to 6. Now let's plug in our 6's. Arcsine of 1 is pi over 2 minus arcsine of -1. That's -pi over 2. and this equals pi. And what was I supposed to do? I am missing something here. All of that is true. 2's did cancel. I pull out the 6. I believe that part is not actually there. I think it's just this part. I don't remember the exact formula. So this is 6 times this. 6 times this. 6 pi. If we multiply by 2, you get the 12 pi. So this is exactly the way that we need to work these types of problems. These little angled lines, slant lengths if you want to call them. The key was this, was to use these slants instead of just horizontal lines. So I have it here. I'll rewrite it. Suppose f of x is continuous on a closed interval a, b, and differentiable on the open interval a, b, then the arc length of f of x on a, b is given by, now this letter I don't understand, but I'm putting it anyways. S. The letter S is used for arc length. I'm sorry. I guess it's something that you got to get used to. It's used everywhere. It probably has some sort of a navigational connection from years past. Whatever the case may be. You go from A to B, and then we have 1 plus f prime of x squared dx. That's one version of the formula. Second version of the formula is actually no different, but if you are a fan of Leibniz notation, you can instead use dy over dx. I want to note one thing here. Let me go back to this example. I just happen to think of it because of the term continuous. This function, let's go right here. Doesn't matter where you're at. The fact is, if you try to throw 6 into this problem, or negative 6, you'll get a 0 in the denominator. The function here that's inside is actually not continuous on the interval because the left and right hand endpoints, you can't plug them in. They aren't there. The function increases to infinity left or right. But somehow the integral still exists. I should probably make a note that when I go from this step to this step, it's called an improper integral. Actually, this is the improper integral. This is what we do with it, which is actually no different than what you normally do with it. The reason why it's called improper is because the function that you're integrating is supposed to be continuous on the interval, or at least what they call integrable. And it turns out that it is, but it involves doing limits and things like that that we will see later in the semester. So, to see later. For now, we'll live with it. None of the problems should be of anything that is even of this weirdness, I guess is the best way to put it. You notice we didn't do anything special. I didn't even think about the 6 and the negative 6 when I plugged them in. But you should, of course. So anyways, our method that we're going to use for the arc length, the letter S, are going to be either one of these. It just depends. If I'm given f of x, I'll use this guy. If the function is given y equal to something, I'll use this. So we'll go ahead and do some examples with those. Let me illustrate this method with a simple first example. Let's compute the length of the line segment that connects two points let's call them x1, y1, x2, y2. Now we already know the distance between them. There's a formula for that, but we know that the equation of the line connecting those points is y2 equals y2 minus y1 over x2 minus x1 times x2 minus x1 plus y1. Now I want to change this to any equation, so I'm going to change this y2 to just y. You can actually change any of them to y if you want to. Change that y2 to y and leave that one alone. Actually, you know what? I'm going to leave this y2 there because this, you probably realize, is m. But the x2 I'll change to just x because I want to be able to vary it. So you get a formula something like this. Now, if I want the length of the line segment that connects them, then the x values go from x1 to x2. So what I'm going to get is this. I'm going to get an integral that goes from x1 to x2, square root of 1 plus, now I want f prime of x, that quantity squared, dx. That equals f prime of x. Well, for this part, if you take the derivative of this stuff right here, that's just 1. The others, that'll just be 0. So you're going to get just m. So you're going to get the integral from x1 to x2 square root of 1 plus m squared. Well, this is just a number. M is constant for a line, so I can bring that out front. And of course, this then is just going to be x2 minus x1. So I end up with the square root of 1 plus m squared times x2 minus x1. All right. Well then, let's go back to the original thing itself. The points were as follows. They were x1, y1, x2, y2, and the distance between them, which would be the length of the line segment connecting them, looks like x1 minus x2 squared plus y1 minus y2 squared. Now, what I'm going to do is factor out x1 minus x2 squared, the squared. Alright, since x2, I didn't really say, did I, which one was bigger or which one was smaller. I guess it really doesn't matter, to be honest, as so long as, if I assume that x1 is the bigger of the two, or if x2 is the bigger of the two, I'm going to get, I'll make it so it matches what's up there. 1 plus. Now, either way, if this is equal to m, the slope of the line, so that's going to be m squared. And then this will be x2 minus x1 if I just assume x2 is bigger than x1. So that gives me the exact same answer that I had before. Okay, so we see this works on the simplest of situations. Let's do a more complicated example. Calculate the arc length of y equals 1/3 x to the 3/2 minus x to the 1/2 on the closed interval for 16. Well, for this one then, I think since it's given in terms of y and not f of x, I'll go with the Leibniz version of the arc length. So they're nice enough to give us the interval that it's defined as. So for 4 to 16, then I have 1 plus f prime of x, that quantity is squared, dx. What is that? I just said Leibniz, but I didn't use Leibniz, did I? Dy over dx. So if I take the derivative of this, the 3/2 times the 1/3 will give me 1/2, because the 3's will cancel out. So I have 1/2 x to the 1/2 minus, now then the 1/2 will come down here, minus 1/2 x to the negative 1/2. That quantity will be squared, dx. Now, your professor is going to crawl on a soapbox right now, because some students will go through the effort, I don't know if you call it effort, no effort. They'll simply drop this 2 and square everything that's inside. And hopefully you realize that's terrible, because you have to work this by foiling everything around. Do you remember the FOIL method? F-O-I-L, first, outer, inner, last. Well, that's how you multiply it out. And I'm going to write the details so that you can see them. So the first thing you're going to have is the first, which would be this thing times itself. So I'm going to get 1/4 x to the 1. And then you're going to have the outer thing, which will be this. This thing times this thing. So I'm going to get 1/4 x to the 0. So minus 1/4 x to the 0. And then the inner, which will be this thing times this thing. Well, it's the same thing again. So I have negative 1/4, that's x to the 0, not sub-0, that's to the 0. Finally, then I'll have this plus this quantity squared. So I get plus 1/4 x to the negative 1 dx. And let me do, obviously, some simplification will be nice. I got 1. This is just 1/4 x. I'll write it as x over 4. X to the 0 will be 1, so I'll have minus 1/4 minus 1/4 plus 1 over 4x dx. And I guess I'll simplify in whatever way is convenient to me at the time. I happen to see that I can do 1 and negative 1/4 and negative 1/4 will end up being 1/2. That the square root of 1/2 plus x over 4 plus 1 over 4x dx. Now, I know of several different things that I could do to speed up things, but I'm going to go in a process that is very basic and elemental. What I'm going to do with these fractions is simply get a common denominator for all of them. What would be a common denominator? Well, 4x will work. It would be easy to make all of them over 4x. So I get the integral from 4 to 16. If I make this over 4x, I'm going to get 2x over 4x. Then if I want to make this over 4x, I'm going to get x squared over 4x, and then plus 1 over 4x. Let me go ahead and put the numerator all together in descending power order to make it easier for me to recognize any patterns. And I do see a pattern. This here is x plus 1 squared. So I have the integral from 4 to 16 of x plus 1 squared over 4x dx. Then the square root of something squared is that, the absolute value of that thing. But x is strictly positive for this problem since it's between 4 and 16. So there's no question that I can simply drop those absolute values and go from 4 to 16, x plus 1 over the square root of 4x dx. Of course, the square root of 4 is equal to 2, so the last thing I'm going to do before I finally finish this thing off is rewrite it like the following. Okay. Radicals, not very useful in the context of problems, so I'm going to change this and also at the same time break up the fractions. Then I'm going to rewrite everything in terms of powers, and I'll end up with 1/2 the integral from 4 to 16. This will be x to the 1/2. This over here will be x to the negative 1/2. Integrate, I'll have 1/2. X to the 1/2 will become x to the 2/3 x to the 3/2. So 2/3 x to the 3/2 plus, and then this thing will become 2x to the 1/2. And that is going from 4 to 16. I can do a little simplifying. If I take this 1/2 and multiply it through, I can just take these 2's out of there. So anyways, what I'm going to have then is 1/3 times 16 to the 3/2 plus 4 to the 1/2 minus 1/3 times 4 to the 3/2 plus, stop, thank you for telling me about that, 16 to the 1/2 minus 1/3 4 to the 3/2 plus 4 to the 1/2. That equals 1/3 times, I like to do the fractional part of the power first. So 16 to the 1/2 is 4. Then you take 4 to the 3rd power and you get 64 plus 4 minus, here 4 to the 1/2 is 2. 2 cubed is 8. So I'm at 1/3 times 8 plus 2. So I have 64 over 3 plus 4 minus 8 over 3 minus 2. That will equal 56 over 3 plus 2. Now if you think of the 2 as 6 over 3, I'll end up with 62 over 3. Or for those that prefer the decimal version, I have 20.6 with a bar over it. For the next example, I'm going to look at one that you don't have the ability to do just yet. I'll show you, but you can get the answer anyways. So compute the arc length of y equals sine of x on 0 to pi. Well, easy enough. We have the integral from 0 to pi, the square root of 1 plus the derivative of sine is cosine, so you're going to get cosine squared of x dx. Now, unfortunately, we do not have the means to do something like this by hand. And usually in the context of the problem, if I expect you to do it by hand, I will let you know that. Or if you can get a decimal approximation, let me show you how that's done. You can do that on your calculators by using the TI versions of calculators. Any graphing calculator nowadays will do this stuff. Alright, so turn your calculator on and go to Y1. Now, like I do, you probably have stuff in there, so let's clear it out. Clear out all of them. I don't want to see any other graph but the one I'm working on. Now, this is not the graph of the original function. You're going to graph the integrand. So put in there the square root. Let's see, the square root is above x squared. The square root of 1 plus. Now, I don't know if it'll do cosine correct unless you put parentheses around it. So I'm going to put cosine of x, and then I'm going to finish the parenthesis around x. I'm going to finish the parenthesis around the cosine part of it, and then I'm going to square that. If you notice, the vinculum for the square root sign has increased to accommodate what I want. If I was going to do more stuff, I would hit the arrow key to get out of that. But let me hit enter. Now we need to go from 0 to pi. So let me set the window x min -1. I just need some operating room to the left of it. And then I could do this 5. That's fine. What else do I want? The y values, I don't know. Let's just take a look at the graph and see what happens. Beautiful. Okay, I want to compute the integral of this over 0 to pi. So if you remember, hit the second key, the blue button, and click trace, and you're brought up to the calculus menu. So click number 7, for the integral, and it's the first thing it wants is a lower limit. You can type in 0 and hit enter, and then it will ask you for the upper limit. In this case, it's pi. Where is pi on this calculator? It is above the arrow key, so you go second arrow, enter, and what it'll do is it'll fill in and show you the region that it's shaded in, and it says here about 3.820 to 3 decimal places. Then this is approximately 3.820. That's the nature of problems like this. They quickly get into situations that can't be integrated. Well, that's usually the case in calculus books. Most real-life integrals are not something that you can actually do with a formula. However, you will always be able to do some sort of an approximation as close to the actual answer as you need to be. Just let the computer give you more decimal places. All right, for example 4, I personally won't do much in the way with this, but it's good to know how to work with it. Compute the arc length. For x equals 1/4 y to the 4th plus 1 over 8y squared on 1 less than or equal to y less than or equal to 2. Basically, there's anything different than what we've done before. I'll come to the problem in a minute. You should remember that the differential dy was defined to be dy over dx times delta x. Well, the change in x is the same as dx. So you'd have dy equals dy over dx times dx. It almost looks like the dx's can cancel, and the notation is meant to be that way. So if you look at an arc length for some problem, you'll have 1 plus dy over dx squared. It's all meant to be able to be this kind of algebra to be done with it. That's the whole point of this. All right, now, if I take the dx, bring it inside, dx inside of the square root becomes dx squared. That means that dx squared times this will get rid of the dx squared in the denominator. Now, because of stuff like this, you can do all the algebra that you think that you want to do. You can actually feel like you can cancel these things out and do everything like that that you want. So with that in mind, this time I'm going to factor out dy squared. So I'll get dx squared over dy squared plus, I should put parentheses around it because this notation takes on a different meaning later on, but hopefully, yeah, I'll just assume dy is positive. And then and you can see it's exactly the same kind of a thing. If x happens to be a function of y instead, then we're going to use this formula for the arc length. So it's just dx over dy. So in this problem then, x is a function of y. Y is the independent variable here. I'm even telling you where y is starting and ending. So with all that information, you don't want to, and you can't. If you try to solve this for x, or solve it for y, well, I don't know if it'd even be possible to do it by hand. It wouldn't be pleasant by any stretch of the imagination anyways. So let's just treat x as a function of y and take derivatives as we know. So let me go ahead and write x again down here. X equals 1/4 y to the 4th plus 1/8. I'm going to rewrite this as y to the -2. So dx over dy equals, bring down the 4, and I'll have y cubed plus, well, a little bit premature there, minus, because of that negative exponent, I'll get -1/4 y to the -3. And so the arc length then is going to go from 1 to 2. I'm going to get 1 plus y cubed minus 1/4 y to the -3 squared dy. Now, I will say go back to, which example was it where I did it? The only reason I'm doing this, I'm not trying to make you sick. But let's go back right here. See this one? This was example 2. Look at the similarity here. Very similar. So, come back to this problem. Use that as your inspiration for this. And figure out how to integrate this thing. It's not going to be pain-free. You're going to have to multiply things out and whatnot. But there is possibly an exact answer waiting for you when you get done. Try not to do it in such a way as to just let your calculator give you the answer and you walk away from it. That's not good enough, because part of what's in this course is teaching you how to compute integrals that are more complicated to do from the ones in the past semester. So it's quite possible that this one could be used, a problem like this could be specifically used to test your ability to do an integral by hand. So make sure that you can get the answer even though your calculator can do it for you.